Hi everyone. Somehow it's not allowing me to focus on one particular slide. And all of that, like there's dedicated FPGA. One platform where each software, like hardware is separate, that is a separate entity, but smart things are different. So the topic that I'm covering is Userspace IO with VFIO. So basically, what is Userspace IO, right? So it is giving the device direct access to the device from the user space, and it's basically unprivileged access also, right? So there is no kernel driver involved, and use cases are many, like DPDK or industrial PCI devices, where you don't really want to write kernel driver for every type of device, which basically does very minimal things, which can be done in the user space also. No, it's in presentation. Oh. Both sides is showing the sticker. Yeah. What if you do this exchange? Exchange I did actually. Oh, just click on slides. Yeah, that interesting thing is all the other workloads which can save us customers. The target like hardware blocks in the thing, like not networking critical stuff. So PDF, yeah. So as I was telling, so for user space IO, the use cases are many. Like it can be industrial PCI devices with very minimal things to do in the kernel, or it may be very sophisticated high-speed networking devices, or networking applications, or things like the DPDK, where you want to do everything in the user space and even avoid interrupts and switch to pole mode, interrupt handling and things like that. So with that in the place, so what is there in the Linux kernel which enables it, right? So so the legacy approaches, one is the UIO, which is the bare minimum infrastructure which is there, which has been there from very early versions of Linux, and that infrastructure is there for all types of buses, a lot of them. And here I'm mostly focusing on the PCI side. So PCI generic is the driver which basically has very limited device support. Basically, it allows the user to map the bars on the PCI card, and then the interrupt is basically Intex is supported, the line LSI is supported, and no MSI or no MSIX or any of that. Basically, the user will open the device file, and if it whenever the interrupt comes, will get the read returns. So that's what is supported, and that's the bare minimum thing. And then for any sophisticated things like DMA or anything, you have to have your own custom driver built into the UIO itself, and it is not. It is a bit hard, and when the initial times of SRIOV and these high-speed networking applications came into play, the proposals were in place to basically extend the UIO PCI generic driver to make it work with the virtual functions and things like that. So that is when this whole switching to VFIO came into play, and this works wholly with the root privileges, because of the whole access is from the sysfs, and there is no separate device file or anything that is around to play around with the user permissions. Then at the same time, there was the KVM. The pass-through use cases have been for the KVM and virtualization, right? So that at that time, the IOMMU groups were also the IOMMU support, as in most of the platforms, it was just in the nascent stages, and the isolations that the IOMMU groups provide, as in what is the IO virtual address space which a device can actually DMA into, whether that is for its own address space, or it is actually allowing the whole system RAM or things like that. So that was not there with even KVM device assignment methodology which existed back then. And with that, even the KVM device assignment back then did not have the interrupt remap support, or even the MMIO remapping support. And QEMU had bare minimum assigned device semantics, which basically would get the bars mapped to the guest virtual address space, and then the interrupts also were getting handled using normal IRQFD, which could poll and look for interrupts and then redirect the interrupt into the guest. And so at that time, these two things coincided, and then the VFIO design came into play. Someone, Tom Newell from Cisco, wrote the VFIO driver at that time, like 2011 or so. And it actually considered all the cases that was the need of the time. So the device should be accessible from the user space with different user privileges, and also that it should support all interrupt types and custom mapping of the bars, and with IOMMU and the DMA isolation. That is what the VFIO solved the problem of the day. And this is how the VFIO presents itself to the user space. So basically, a container, the whole concept around VFIO is with the VFIO containers, which is basically the collection of IOMMU groups one would get access to. So basically, create a container and then add IOMMU groups into that. And IOMMU group here is the group of devices which share similar isolation. What do you say? Similar isolation properties. One is IO virtual address space, and the other is the devices which are under the same PCI root controller, which has the ACS support to prevent illegal access to the other address space. And that is, and this container basically gives you a group of, as the image here shows, right? So these devices are in particular there are two IOMMU groups here, and two devices are in the same IOMMU groups. And this container is accessible to the user space using a FD, and also there is group FD, which is used to add to that particular container, and then individual devices can be accessed using the device FD. And the user space view here is that the user gets to view the devices as a group of regions, a set of regions that are there on the device, and the regions have the property to say whether it can be mapped, unmapped, or whether it can be read, write, or things like that. And the config space is one of the regions therein, and that is not mappable. It provides only read, write access. And so, yeah, the config space allows only the read, write access, and then the interrupt management also is driven through the VFIO IOCTLs. VFIO provides all these facilities through set of IOCTLs. And for interrupt also, it does basically have, what do you say, one can query the set of interrupts that the device supports, and it allows someone to set an event FD handler for it, for individual interrupt, so that he gets notified when the device interrupts. And also for QEMU kind of use cases, the KVM, there is a KVM IRQFD which can be linked with it, so that the user space doesn't get the interrupt and the kernel alone gets it, and kernel handles it. The KVM gets it directly. The guest gets it directly. And then, yeah, there are certain nuances around the mapping support, and what do you say? Some of the bars which are not really mappable, or sparse map support has to be there for some of the maps, some of the bars. Like if some of the, like one bar has a MSI region, MSIX table in that, in its bar, the MSIX table should not be mapped. And basically, VFIO prevents that. And for that, you have to map only till the first offset where the MSIX table starts, and then end it. And QEMU takes care of emulating these things. And For normal use cases, yeah, as user can just map as much as he wants and set up the event FD and use the device. And then with the interrupts, it is not just the interrupts that one would want when it comes to using the device from user space. It can be, there are many use cases like the error handling, right? So if the device actually hits a AER or in PPC, it's called EEH, basically some violation of a kind, like you try to attempt to DMA into a region where you are not allowed to do it. So the platform isolates the device and then notifies the user on this particular interrupt handler. Then you are supposed to handle it in a graceful way. So, and also there are request IRQs, like someone wants to unplug the device, then it should not, the user of the device basically gets another kind of an interrupt to say, now is the time I stop using the device gracefully, and then release the device. And there are separate interrupt handlers for all of these, and these are exposed using the VFIO APIs, which the user can configure and use. And then the DMA support also, with the for DMA support, basically for mapping the user address space where we want the card to write, and map and then unmap the DMA buffers basically. So what here the VFIO takes care of pinning those regions, and then also ensuring that the user is not pinning too much, right? It is actually locked. It is actually considered locked memory, and that memory is not available for anyone during the DMA. So even the accounting, the VFIO takes care of it. And yeah, I mean, there are so many features around VFIO that I would say, like, for even it's evolving even today to what do you say? There are so many what do you say, hardware specific kernel drivers. Many of these the VFIO provides the generic features, but there are some features which need the real hardware vendor support. For example, if we want to migrate a particular guest running a particular type of a network card or something, I don't know, so whatever, and we want to migrate that guest to another host, then only the VFI will not know what type of queues are there and what are the real hardware devices that are sitting on the card. And for this, to really restore and save state, and this handshake of finite state machine, right, where you move between the states of getting the device from active state to really pause and then stop dating and those things. For that, there are set of IOPTLs which are supported only with hardware specific VFIO driver support. And the same way, there are a lot of cases where in case of GPUs also, like there is only one IOMME group, but the device can be split across different guests. Basically, for those use cases, there is a concept of mediated device support, which is there with VFIO. So basically, the hardware hardware vendor will actually partition the resources in such a way that the user can actually use this same device, even though they belong to the same IOMME group, across different guests with the assured isolation that is ensured through the MDAV driver. And then, yeah, I mean, there are customizations through specific vendors like SRIOV and all this. How we enable SRIOV on a particular card is known only by the particular vendor. The vendor knows the hardware capabilities, and only the vendor can create the channels that the card actually supports and things like that, which is not duplicate channels, or there may be some firmware initializations that need to happen before enabling the SRIOV on the card. So those things need the need the driver support, and this driver need not be in the kernel alone. So even Userspace can have its own driver, and Userspace driver can also do this SRIOV enablement. That is the. And then other than this, yeah, I mean, things are evolving to an extent where IO virtual address space as such, the VFIO actually for a given IOMME group has always created one IO address space domain and gave it to one guest, kind of a thing, right? Or gave it to a guest for use case. But the use cases are evolving beyond that, with nested virtualization coming into play, where we have a nested guest which wants to have its own address space. So basically, one device should have more than one address space. And so for that, the evolution is going towards the IOMME FT, which is basically exploiting the IOMME features to make VFIO even more advanced. So yeah, that's pretty much I wanted to cover for today. Thank you.
Questions to Shivaprasad?
Is this only through IOCTL or is this a first kind of support also available?
No, most all through IOCTL.
Because I mean, I hear in Linux they are not preferring IOCTL; they're moving away from IOCTL to SysFS.
That is the thing. With SysFS, anyone with root privileges gets complete access. Isolation is lost. If you try SysFS, I mean, basically you can read the bars and map and do those things using the SysFS interfaces, but you lose all the isolation mechanisms that the VFIO provides.
Okay.
Two users can directly map and overwrite each other.
Okay.
This one prevents it.
So this is only through the IOCTL.
This is all through IOCTL.
How DMA works in this case? Don't they need a separate driver?
No, the driver is the user space driver. Basically, you bar the map. You map the bar, and you know where to write to initiate the DMA, right? And all you need is allocating the buffer, which you do in the user space with mmap, and then give that virtual address space to the kernel, asking this as my DMA buffer.
Okay.
You tell the kernel that this is my DMA buffer, and when you write to the controller saying start the DMA now, it actually writes there. The card actually writes there. And the translation of this to the hard physical address and then pinning it, all of it VFIO takes care, basically. And in case, in case of virtualization, even there is one more layer, like converting it to the guest physical address and then to the real physical address. All that is taken care through KVM playing together with this.
Okay.
Yeah, basic question. So this, if you can actually map the device to memory, you can write to it from user space, right? So how is that different from the kernel? It's the same thing, right? It's actually just that you're doing it in user space.
Yes.
Am I right?
Yes, yes. Only thing is this provides you the complete isolation and ownership of the device. And it prevents any
Isolation
any
meaning for
two people trying to control the device.
So two people writing the same code, two threads with the same code will be completely isolated, even though they're accessing the same set of registers.
No, it won't allow. VFIO prevents
It will sequence it or something.
No, it will not even allow.
It will lock it.
Yeah, it will lock it. The container is the one which holds the ownership of the device to one process.
Because of the IOMMU.
That's because of the
Ownership of a
IOMMU.
virtual device, right? Virtualized.
No. Real device.
Real device. Then how you are benefiting from virtualization?
That is where SRIOV and then mediated devices I mentioned will come into play. SRIOV will create multiple virtual functions for you, which you can give to different guests.
Okay.
But the use case for user space IO is different.
But I'm assuming everyone that is using VFIO would be initiating even the register, write, read,
everything,
user space itself.
everything.
And they'll all get their own containers.
Exactly.
Like virtual containers to hit the real device.
Not virtual. It is real container. It is a container. It is an abstract term. And with that, they own the device and they get the real data on the card. Everything is real.
Everything is real.
Yeah.
Will this approach be suitable for real time?
Yes. Yeah. I mean, high-speed networking applications like in toolkits, right? Like DPDK and others. They use VFIO.
Because it's only scheduled, right?
Yeah.
As a process. So
And VFIO is completely going to mask the real driver, which is
there is no real
there's
driver.
no real driver.
The real driver is in the user space. You are the driver.
So you have to write driver code basically.
Yes, exactly.
So when we allocate memory for DMA operation, so who decides what is the threshold value till what we can pin the memory?
One is the user space control, right? That locked memory and those things are there, right? That tells the max limits on the maximum number of open files and things like that, right? You can increase that, and then that is the hard limit.
If you have a C group kind of thing where you can limit the.
Yeah, C group
total
also
number
comes
of
into play.
users.
How much you can allocate and how much you can.
Okay. And can there be multiple container? Container is like IOMMU level, right?
Yeah, it's a abstract term for the IOMMU. It can comprise of more than one IOMMU group also, depending on the driver and the use case.
Okay.
So there is something called use pages that is used by this activity and activity. So is it a requirement of VFIO or is it a requirement of the user space stack?
It is entirely the user space and the use case driven. So if you want to prevent too many map and unmap requests, right? That is when you use the DMA mapping, and also it is basically the card back and right. What is your buffer size, things like that. And many times it is even how much space you have for making these table entries on the IOMMU. If your table is small, you may not be able to fit too many entries. Then you choose a higher page size.
So have you seen the use cases of, these are maybe a user space question. I've seen a lot of 2 MB page use cases.
Yeah.
But there are 1 GB page as well use cases.
Yeah.
So is this getting used in industry?
Yeah, I mean, there are use cases actually. There are many use cases like that.
So IOMMU groups, can you elaborate more on how they actually help?
Yeah, so it is like for virtual IO virtual address space to the real address, right? You need a table to translate that. And how many devices this table stands for is the IOMMU group. They share a common IOMMU table. Where you have it, it depends on different platforms. It varies where it sits, right?
Quick question. I have a network device card and it supports 64 virtual functions. So using VFIO, can I have 64 containers created for it?
Yeah, you
in
can.
different processes?
Yeah, I mean,
And
you
they can run
can run
simultaneously?
64 drivers, applications running as drivers. Yeah.
64.
Yeah.
Okay. And they'll all get their own exact
Their own real
one-to-one
device.
identity with that
Yes,
virtual.
yes.
Okay, got it now.
So everyone will have their own IOMMU group, each application?
Yes, in case of I'm ignoring the mediated device case, they will have their own.
More questions? Yeah, thanks, Shivaprasad. Session. Yeah, so this is the last topic for today, and so we'll meet in the main hall for the closing session. Thank you.